Hello! Welcome to Train Signal. This is common VNX terminology. Now, if you haven't guessed it by now, the VNX is an intelligent storage system. Now, what makes it intelligent? What do you think? I think it's software. Software makes everything intelligent, right? But there's also some other components that are key elements in understanding what an intelligent storage system really provides. That's things like the backend. That's your connectivity between your SPs and your disks themselves. That is considered the quote-unquote backend. That is that SAS bus interconnect between those two. Your front end is really what your hosts are connecting to over your network, either over your IP network, your Ethernet network, or a fiber channel network. And those front end ports can consist of fiber channel ports. 8 gig is common nowadays. Could be copper, Ethernet ports. You've got a couple different options, even 10 gig, and they're all coming in across those front end ports because they talk data center protocols such as fiber channel, FCOE, and then they're hitting cache directly, which is really the next component of this. So data that is written to the front end usually hits cache first, and then an acknowledgement is sent back to the host itself. Another major component of the intelligent storage system is the disk, the backend disk. So all four of these together with software kind of automating and steering and managing all of this is what makes up an intelligent storage system. So let's get into some of the terminology. Now, these are things that I thought were very important to understanding really the mid-range line from an EMC perspective. Now, some of this stuff can be applied to other vendors as well, but it really is applied to EMC, and you'll see that some of these things are only common to EMC themselves. Now, defining an active-passive array. When you think of, at least from the Clarion perspective, if you ask anybody from EMC, they may say that really that active-passive terminology went away when the CX went away and the VNX replaced it. It's hard to say that. Active-passive is really not as easy to define as you would think. Sometimes it's seen as a negative. Sometimes active-active always gets all the glory because especially in situations where you have failed components, that's really when active-active pays for itself, because you're able to provide the same level of performance even though you've lost maybe a hardware component. With active-passive, if you lose one of your major heads, one of your SPs, you're going to suffer. Okay, it's not common for you to have LUN ownership, all your LUNs sitting on a single SP. Usually it's balanced across your SPs. So if you lose a single SP, well, now you're at 50% performance, right? That's not common on the higher end arrays, so it does get sometimes seen as a negative. Now, LUN ownership in itself, when you go out and you create a LUN, and that LUN is really the raw data that you're handing up to your host, and then your host puts a file system on it, that LUN ownership is only owned and serviced by one SP at a time. All right, that is the simplest way to state an active-passive array. Right? You have LUN ownership. It's owned by a given SP. That means your host is actually transmitting I/O across one SP at a time. Now, when you add in something such as ALUA, asymmetric logical unit access, this really changes the way how active-passive operates. But does it really? LUN ownership is still defined to a single SP. So with ALUA, the best way for me to describe this, and this is a very common diagram when it comes to ALUA itself, it's not something that I developed, but if you look at it from this perspective, if I have a host, he's sitting at the top, and I have my big blue LUN at the bottom, normal access would be that far double arrowed line off to the right there. So the host would hit SPB, and then SPB owns that big blue LUN, and that's how he's accessing. He's going through his paths that are allocated through SPB. Now, if you lost SPB just died. In normal situations, without ALUA, any LUNs that were owned by SPB now get failed over to SPA. And you'll see the host itself actually has access to both SPs. Okay, so that's to give him the ability to access that big blue LUN across either SP in case one of them dies, so it's not a single point of failure. The double-headed arrow on the left-hand side is how ALUA would access that big blue LUN if for instance, say SPB lost some ports that the host was accessing that big blue LUN on. So it doesn't really help you, and this is kind of mentioned down here on the third bullet point. LUA doesn't help you if you lose an SP in its entirety. There's no benefit with having a LUA in place. The benefit comes when you lose front-end connectivity to SPB in this example. Then the host can access that LUN that is owned by SPB via SPA across that interconnect, that internal messaging interconnect between A and B. So its path to that LUN is really host to SPA, from SPA to SPB, then down to LUN. So LUN ownership never changes hands with a LUA in play. You lose an SP, doesn't matter. You lose B, everything trespasses or moves, migrates, whatever you want to call it, over to SPA. Now that host is accessing that big blue LUN across SPA. That's how it works. Now, there's this notion within ALUA of optimal and non-optimal I/O transmissions. Okay, so optimal access to that big blue LUN would be across SPB in this example. Non-optimal would be across SPA. So that's a very common terminology with ALUA itself, optimal and non-optimal pathing. You actually see once we get into the interface within the lab itself, it actually says optimal and non-optimal. It shows you that information within the GUI itself. Symmetric active-active, so SAA, this would be AAA array. So a typical VNX would be an AAA array. This would be Symmetrics or VMAX would be a SAA array. That's able to provide active-active connectivity to a LUN at any one time. So it's actually able to traverse multiple controllers or directors and get access to that LUN on the back end, that big blue LUN, right? And this just gives you increased throughput. It also gives you the ability to sustain the performance that you were used to prior to that component failure if you were to lose a hardware component or a director or whatnot. So what I want you to take from this slide is that EMC markets the VNX as an active-active array, but it is an asymmetric active-active array. And what makes it asymmetric is ALUA, is the LUA failover capabilities. But to me, it still is an active-passive array. That LUN is still owned by a single SP at a time. So what's the front end? The front end, you should know what the front end is. It's really the conduit between your host and your storage array. Now these are all controller based. They're copper and fiber channel ports, and on those ports they're able to process common data center protocols. Right? So you've got, you're able to read, if you've got fiber channel ports, you're talking fiber channel across those fiber channel ports. If you've got iSCSI ports, you're talking iSCSI across those copper ports. Same with FCOE. The front end ports itself are handling incoming data from your host, and they're handing them off to cache. Cache is going to be their first dumping ground on the array itself, and then that acknowledgement is sent back to the host. Then over time, that data in cache gets destaged, what's called destaged, to the back-end disk, where it's kind of its final resting location. So we want data in cache. The more cache you have, it's typically better, and that's why you see things like fast cache that come into play that allow you to utilize your EFDs for a secondary cache tier, because we want data in cache. It's going to be received and accessed a lot quicker than a mechanical spinning disk. The back end, this is the conduit between cache and your physical drives. This is the SASN bus transport that's between your SPs and the DAEs themselves, or your disks themselves. This replaced the fiber channel arbitrator loop of previous arrays on the CX line. I mean, it really is ridiculous on how fast it is in comparison. Huge improvements from previous generations. Much needed change. Fiber channel arbitrator loop was simply not capable of handling a lot of the new disk technologies coming in. So SAS backend bus is certainly capable of that. From a backend perspective, you're doing error detection, soft errors, hard error, media writes, things of that nature, error correction, and all your rating takes place on the backend as well. Now the vault drives, the vault drives have been around for years. So ever since I've dealt with EMC mid-range arrays, the vault drives have always been in place. It's just a common building block. It's just the way the arrays are architected. On the 5100, the 5300, and the 5500, which have, if you remember correctly, have the DPE, right? So it's really the collapsing of the SPs and the first DAE into one enclosure. On the DPE, your first 4 drives would be your vault drives. Now on the higher end arrays, the 5700 and the 7500, where you have an SPE, the vault drives are not included in the SPE because there is no drives in the SPE. Right? Your first DAE is essentially DAE 0. It's enclosure 0. Your vault drives are going to be the first 4 drives in bus 0, enclosure 0 on the higher end arrays. This is an area reserved for the operating system. It's where VNX OE for block lives. It's also where the cache vault lives. Now, what the cache vault provides is a D-stage area for your hot data, your cache, in case of power loss on the array itself. So you have data that's coming in from your host, and it's coming across multiple protocols, maybe on, especially on the SPs. If it's coming across as FCOE, iSCSI, or Fiber Channel, that data is always going to be written to cache first in most scenarios. At that point in time, if you lose power to the SPs and the array itself, you have a finite amount of time where that data in cache needs to be written to disk. And that's where the cache vault comes into play. That's where it has enough capacity where it's able to write the data that exists in cache, which is going to be all your hot data. It has enough capacity to be able to write that data to the cache vault itself. Now, with the vault drives, I didn't mention earlier, but with the vault drives, 192 gig off each disk, each of those 4 disks is consumed for these capabilities, both the operating system and the cache vault itself. Now, there's some other things in there as well that I haven't mentioned that I won't get into, but I wanted to mention those are the 2 providers of what the vault drives give you. So just keep that in mind. You are losing capacity on the first four drives, and normally you would not put any data on the first 4 drives for a number of reasons. But as you add more things that may be more I/O intensive on the vault drives themselves, could it potentially affect the performance of the array? So you really want to keep things off of there unless they're pretty stagnant. I've commonly used them for ISOs, data storage within a VMware environment, also templates. A lot of the times, maybe it's a pretty stagnant environment as how much you're deploying within your data center. You may want to put those template data stores, those ISO data stores on the vault drives themselves. Also, your control LUNs for your data movers themselves will go on the vault drives, typically. Storage groups. This, in short, is LUN masking. I'm saying I have a LUN, and I want this LUN to be seen by these particular hosts. That's it. Everything else, I don't want to see these LUNs. Why would you do that? Well, do you want a Windows host to be able to access a VMFS volume on the VMware side? No, you do not. And there's a lot of, there's, all these operating systems typically may have different types of proprietary file systems that they use. So you don't want a system that's outside of that OS to be able to access a file system that it does not recognize, especially from a Windows perspective, because it will grab that LUN, it will just interrogate it, and it will just do things with it that you don't even want to know about. So that's why we have storage groups set up. Okay, so it's for this LUN masking capabilities. Now, it's a feature that allows LUN access to some hosts and disallows access to other hosts. Now, one common thing with storage groups is that a host can only live in a single storage group at one time. So you couldn't take an ESXi host and put him into multiple storage groups. The flip side to that is that you could take a LUN that ESXi host and sees and put it into multiple storage groups. A common scenario over this would be boot from SAN LUNs, in blade environments, where each boot from SAN host needs to see and only see its boot LUN for booting up. It's got the operating system on that boot LUN. But you don't want any other host to see that boot LUN. But you do want to give every other host or all the hosts access to common shared VMFS data store. So how do you do that? Well, on the VNX side, you would have a storage group for each host. And in that storage group, you would have a single boot LUN that only that host can see, but you would have all the VMFS shared data stores across all the storage groups. That's very common. We see that a lot nowadays. And that's really how you do it. I mean, it's not that we've come up with that or anything. That is how you do boot from SAN LUNs, in particular with blade servers. So defining traditional RAID groups. This is what EMC's been doing for years on their block arrays, right? It's just you're pulling together or grouping together disks, up to 16 disk increments, and you're applying array technology. Now, usually there are preferred discounts within certain RAID types. They have what's called 4+1s and 8+1s. These are common RAID groups for RAID 5. There are certain discounts that you would want if you're doing one particular RAID group over another. The RAID groups that are supported on traditional RAID groups are 0, 1, 10, 3, 5, and 6. Now, the max number of disks you could put into a RAID group is 16. You'll see this is vastly different on the storage pool side. We'll see at the next slide is that you have a finite amount of disks, a very small number of disks that you could put into a RAID group itself, but you do have the ability to do isolated type setups where if you wanted to go in and you wanted to create a RAID group just for transaction logs for a single SQL server, you could do that and not burn up a lot of space, and certainly not have that in a shared environment such as storage pools would offer. So there is very much a common use case for traditional RAID groups. For the longest time, we were using traditional RAID groups for things such as journal volumes on recovery point and things of that nature. There's also other scenarios you would use traditional RAID groups, so don't completely discount them in your designs. Know that they are there to provide that isolated performance in situations where you need it, where it doesn't, maybe a LUN doesn't serve best in a traditional storage pool environment. All this talk of storage pools, what are they? You have file and block storage pools, and you'll see this once we get into Unisphere. You do have the ability to be able to carve up storage pools from the block perspective and create LUNs on it. And then you do have the ability to create storage pools on the file side and create file systems on it. Now, to add another layer of complexity to that, you also can create storage pools, create LUNs on those storage pools, then push those LUNs up to the data movers themselves, create another type of storage pool, and then within that storage pool on the file side, create file systems. So you can do that as well. A lot of different layers of abstraction, if you will, to be able to accomplish that, but certainly very prevalent in our customers' environments today. Pools are just a bunch of disks with applied RAID technology, right? So with traditional RAID groups, we had a set number of disks that we could provide in a traditional RAID group of 16, the max. With storage pools, you can provide hundreds of drives within a storage pool. Now, some of those numbers depend on the models that you're running these storage pools from, so that's why I didn't put in an exact number there. But just know it gives us the ability to pull together disks, apply RAID technology, and it is much larger than a traditional RAID group. Now, there's these what's called private RAID groups and LUNs that really underpin these storage pools themselves. For instance, if you had a 10-disk storage pool, you would have a private RAID group. You would have two private RAID groups. If this is a RAID 5 storage pool, you'd have two private RAID groups, two 4+1. So that's commonly how a RAID 5 RAID group is referred to as a 4+1. You have 4 disks for data, 1 for parity. It's just the common technology in the storage, or a common terminology in the storage world. So you would have two private RAID groups underpinning that 10-disk storage pool. Then on top of that, and this may have changed in Flare 32, but on top of that, you would have private LUNs that are actually created on the fly or on top of those RAID groups, those private RAID groups. And then that capacity is served up into the interface, and then you create your data LUNs on top of that storage pool. Very confusing process. It is how storage pools themselves are architected. Multiple RAID groups in VNX OE32, you now can have multiple RAID types within a storage pool itself. That was just not common in anything prior to 32. When you define the storage pool itself, you define the RAID type at that time. If you want to do fast, which is fully automated storage tiering, you have to be in a storage pool itself. You cannot do this across traditional RAID groups. We do all of this, why? So we can create LUNs. If you're talking storage and you're talking block storage, you're talking about the LUN, and that's That is really the logical construct, that we decide the capacity of that LUN based on the pool that we're creating that LUN out of. So we may have time space within a pool or a traditional array group. We're carving up the size of the LUN based on our requirements from a host perspective. And like I said, it is a logical construct. You do designate either one or multiple disks underneath with an applied RAID technology. This is central to block-based storage. When you talk about block-based storage, you talk about LUNs. Now, the compression and deduplication, at least compression is applied on both sides of the array, meaning both file and block perspective. Now, these are space efficiency technologies. Compression is available on the block and file side. Deduplication is only available on the file side of the VNX. So keep that in mind when you're designing out there. Both of these operations occur when data is at rest. So if things haven't been accessed in a set amount of time or they haven't been modified in a set amount of time, that's when you would apply compression and deduplication. It's usually not for hot data out there. This could impede the performance if that data is compressed and it has to decompress it as part of an operation that a host is trying to access that data, or even deduplication. If you are accessing data that's been deduped or compressed, it could be a bit of a delay for doing that. So you do want to make sure that is occurring data that is at rest and not frequently utilized. It is an asynchronous operation. It's only available on the 5300s and above, so it's not available on the 5100. So what's a hot spare? A hot spare is global in nature, and it allows you to protect a failed drive of equal size or less across the array. So if you have a 3 terabyte nearline SAS drive, you have to have a 3 terabyte nearline SAS drive hot spare to be able to protect it. If you have a 3 terabyte nearline SAS drive that is a hot spare and you lose a 2 terabyte nearline SAS drive, then that 3 terabyte nearline SAS drive can protect the 2 terabytes. So that's what that statement is saying. Another component of that is that if it has to be the same drive type. So you couldn't have a nearline SAS drive hot spare a SAS drive. So therefore you have to have a hot spare for every drive type. You have to have a hot spare for your largest capacity drive within that drive type. And then the normal rule of thumb is to have a hot spare for every 30 drives in your array itself. So those are some of the design aspects when it comes to hot spares. Now, what does a hot spare do? It assumes the identity of the failed drive. In parity RAID types, the data is rebuilt on the hot spare from the surviving drives. For mirrored RAID types, data is copied from the survivor mirror member to the hot spare. Now, when you replace that failed drive, things kind of take place in reverse. Data is copied from the hot spare to the new drive, and then once that's done, the hot spare is returned to a normal idle operation and therefore is able to serve out or hot spare other failed drives. So hot spares, I believe are common across most vendor arrays. The VNX is no different, but certainly something that is desired. Don't configure your production arrays without hot spares. This is the lab portion of the lesson. We'll take a look as it's applied within Unisphere, some of the common VNX terminology that we went over. So we'll log into the Unisphere. One of the first things that we'll look at is the ALUA-based settings. So asymmetric LUN unit access, logical unit access. We'll take a look at where you actually set that. So if we go to the array itself within this first dashboard we see, and we right-click and we go to connectivity status. This is going to show us our initiator records, our hosts that are actually logged into the array itself. Okay? And initiators, you're going to see multiple initiators assigned to a host. Now, these hosts in particular, they're ESXi 5 hosts. So when they log into the array itself, they automatically self-register. Okay? And they pull the host name from the host directly, and they log that in this entry. Most often when you're doing the zoning and you're zoning a host to the VNX or the CX series, the registration does not take place automatically. Now the caveat to that is if you have a Unisphere client on the system that's actually connecting, it will register what the name of that host is and what the IP address of that host is. More times than not, if you don't have the clients on there, it will not self-register and you'd have to go in and manually register. But this is a ESXi 5 host, so we don't have to worry about that. But if I take a look at the initiator record itself and I go to edit, You'll see a couple different things here. Now, I could edit this initiator if I wanted to, but I'm not. I'm going to show you a couple different bits of information here as it applies to this record in general. Now, you could go in here and set the different initiator type, and more times than not, clear open is the primary initiator type that we're using in most environments. You also see recovery point in here. So if we're doing a recovery point installation, the initiator records need to be recovery point appliance. But most often, and what's common in a lot of the environments that we see is that clear and open is usually the initiator type. And then failover mode is failover mode 4. Failover mode 4 is ALUA. It is ALUA based. It gives you this non-optimized and optimized pathing if there's issue with an owning SP for a given LUN. That is by default. That was the first option there. That's the one it selects. So that's what you would want to use if you're running a VNX and you're zoning to the VNX for a host. You would want to use ALUA. There are some caveats to that, but more times than not, ALUA is the route you want to go. How I would tell that for a given initiator that it's already logged in, if I clicked on the initiator itself, hit detailed, I could see that the failover mode here is 4. So I know this is configured for ALUA. Now, if for some reason I logged in and the initiator failover mode was set to 1 and I wanted to change it to 4, well, this would be how you would do it. Come over here, you click on the array itself, go to host, go to failover wizard, and this little wizard right here with wizard and all will allow you to change the failover mode from its given whatever it's currently set to as far as the failover mode, and will allow you to change it to whatever you want. So for instance 6, I could go in here, select vSphere 6, hit next, select the array, next, and then you'll see the same information that we were presented with on a couple previous screens. So I could change the initiator type to Clarion open, could change the failover mode to 4 or any other failover mode I wanted to. And then I can set the array com path, which is enabled by default. It was actually an advanced setting on the previous screen. You didn't see it. And then you go next, next, and then finish, and then that would change the initiator records for the given host. Now, if it's an ESXi server, I would recommend throwing it into maintenance mode, then running this, and then either rebooting it or removing it from its current storage group, which we'll go over here in a second, the LUN masking piece, and adding it back into the storage group. And this will change what's called the SATP, the storage array type plugin within ESXi itself. And it's going to be how it actually handles failovers. Can't remember how the terminology for some of the SATPs, but it's like VNX underscore SATP VMW or something like that. It changes the SATP and it changes how it actually handles failover within the PSA or the pluggable storage architecture within ESXi. So we'll hit cancel here, hit yes. We'll move into the front end and the back end. Where you can view that information is under System, and we'll go to Storage Hardware, which denotes block storage hardware. And if I go to SPs, kind of drill down in here, this is a multi-click process. I can see that I can see my slicks in here, my A0 and A1, and if I go to Properties for this, I can see that this is a fiber channel slick. It's got 4 ports. They're actually negotiating at 4 gigabit for whatever reason. The max is 8 gigabit. I can also see how many logged in initiators that I have. Okay, so these are hosts that are actually logged into the front end ports on this array themselves. Now this is your fan-in ratio. How many ports are coming into one port on a VNX? And each of these guys are going to have different fan-in ratios or different registered initiators on here, if there's any host zone to them. So this one is. This one does not. And I would assume this one does not either. So that gives you some fan-in ratio. Then I can, if I want to look at the actual SAS backend information, not too much to really show you here, but if you wanted to see, the SAS controller, let me scroll down. This would be presented here. So if I go and I right-click here and I hit Properties, I'll see that the current speed is 6 gigabit per second. I know that this is my connector for the SAS backend bus. So not too much information to show you there. You can find a lot of this information if you're running reports and you want to view your slicks and things of that nature. You can view that via the reporting rather than having to drill down in here and take a look at that. The vault drives will be just as exciting. It's not really much I can show you there. If I go to storage pools, go to RAID groups. Now it really depends on how you've been taught. If you're currently a user of a VNX or a CNX, some person maybe along the way, whether it was a vendor or whether it was EMC themselves or a VAR or someone, they may have said, never use the vault drives for anything. It's just never do it. Don't even configure a RAID group. Well, in most situations, that's okay. You could do that, but as these drives get bigger, and maybe you've allocated 600 gig drives for the vault drives, maybe you want to utilize that space for something, and you certainly can. There's nothing preventing you from doing that. Now, you will lose some capacity off those drives, that 192 gig off each drive that's utilized for your vault cache and the VNX OE itself. That is going to be stripped away. You won't have that space allocated to it. You won't even see it in the GUI. You won't even see it in Unisphere. But you could use that space if you wanted to, and that's what we've done here. If I look at RAID group 0, and I take a look at the disk, I know that the first 4 disks are my vault drives. Right? So I've got bus 0, enclosure 0, disk 0 through 3. I know those are the vault drives. A great use of those drives are boot LUNs. So if you're doing UCS and you're booting ESX from a boot LUN off the VNX, those are great locations. Those vault drives are great locations for those boot LUNs. And that's only 20 gig. I mean, per host is typically what we configure it for. Sometimes smaller, sometimes bigger. But that's really all the space that's utilized. And if you're doing any ISO, if you have an ISO data store, maybe even a template data store, I mean, I know that may be precedent for some of you guys. But that's certainly a good use of that capacity that's built into this that you would maybe normally utilize in that RAID group. Next is the storage groups. We'll take a look at the storage groups themselves. So if I go over here to host, click on storage groups, this is the LUN masking portion of the VNX itself. So LUN masking is really you're allowing certain hosts to see certain LUNs. That's really what you're doing, and to not see other LUNs. So what we've done here is, actually let's take a look at 6 and 7, is that we've allowed 6 and 7, host 6 and 7, to have access to, read-write access to, 4 LUNs. Those are data store 1, 2, and 3, and its boot LUN. Okay. Anything that I put, when I go in here and I register the hosts, and you saw that back on that connectivity status screen, which is right here, I can actually get to it, or at least a portion of it from this perspective. And I can see my initiator records. Once I actually register that host, or he self-registers, EasySXi5, if he self-registers, I can then throw him in this storage group, and then I can create some LUNs and put the LUNs in the storage group as well. That is your LUN masking portion. You're saying this host, vSphere 6, is able to see these LUNs. And only these LUNs. So if you want him to see anything outside of the LUNs that you've presented, you have to add that LUN to this storage group. You have to. You can't have a host, and one of the great rule of thumbs for storage groups is that you can't have a host in multiple storage groups, but you can have a LUN in multiple storage groups. So keep that in mind. So these data stores, 1, 2, and 3, they're in multiple data stores up here. See? So keep that in mind. A host can only exist in one storage group at a time, but multiple LUNs can exist in multiple storage groups. Now let's look at traditional array groups and storage pools. We go to storage here, and I click on storage pools. I've got 2 tabs up here on the left, and they both delineate what they are. The first one in the default to which it opens to is the pool tab, and this is where you would actually create pools. Now if I hit create here, I have the ability to create pools. So here's where I can go in and I can set the pool name, whatever I want that to be, the RAID type. RAID 10, yes, I said 10, 5 and 6. And then I can set different levels of disk performance within the pool itself. So if I have some SSDs, I have some flash drives, I could select those right there. I could select some SAS disks, some nearline SAS. I think that's all I have left is nearline SAS. And then I would go into manual, set it to manual, go to select, and then I would be able to select my drives that I want to add to this pool. So let's just add a couple. Let's add in all of them. I won't actually create it. So I've added my disk down here. So now once I hit apply down here, it's going to go out and it's going to create the storage pool. Now this is going to be a 4+1 RAID 5 storage pool. So I've essentially got 4 disks for data capacity, and then I've got 1 disk for parity. It's actually, the parity is actually spread across all the disks, but for the instance of an example, that's how it is. I can also put a pool description on it. I can set a threshold so that when it hits 70% full on the pool itself, it'll actually send me an email. And I can also enable fast cache. So if you remember, fast cache is this secondary tiering option that allows you to utilize flash disks within your array itself. It is enabled at the global level. The difference between enabling fast cache on pools and RAID groups is, from the pool perspective, you enable it at the pool level. You can't enable it on a per LUN basis. Now you can enable fast cache on a per LUN basis if it's in a traditional RAID group. So keep in mind that if you're designing, you don't have the option of enabling fast cache on a pool LUN basis. It's only on a per LUN basis in RAID groups. We'll go back over here. So the last thing I would do is hit apply. It would create the pool. We're not going to do that right now, but that would be the option there. I can also set a scheduled auto tiering. This would be the fast portion, giving you the ability to tier between different levels of disk types here. Normally you would not turn on auto tiering if you only have one type of disk in there. Then I think that makes sense. But if you did have multiple disks within this pool, you could turn on auto tiering, and then at a predefined time in the day, that data would be moved to specific tiers based on performance that's been captured throughout the day. That's it there. Let's jump over to RAID groups. You try to create a RAID group. Same type of process. You would go to create a RAID group. Remember, as I mentioned in previous slides or lessons, that a RAID group is maxed at 16 disks. You can't put any more than 16 disks within a RAID group. Okay. Now pools, you can put hundreds of disks in the storage pool, depending on the model of array itself. So if I wanted to create a RAID group here, same wizard, except you'll see that it switches when I switch between pool and RAID group. I can give it a number. I can't give it a name. It's predefined as to basically it's called RAID group, and then the number is the suffix on the end there. And then the RAID type, I can set that as well. I can do RAID 1, 1+0, or RAID 10. Yes, I said 10. RAID 3, RAID 5, 6. I could do just a single disk if I wanted to. Or I could do a hot spare as well. So let's say I wanted to, same process, I want to put all these disks in here. I have all my disks around there. It gives me a recommended number. And the nice thing about Unisphere, when you're doing pool creations or RAID groups, that give you the recommended number of disks based on the RAID type that you've configured. You can't change that. So if I set 10, you notice it goes to invalid disk selection because I don't have the recommended number of disks in the RAID group that it would like to see. I'll just flip through some of these other ones here just so you can see that. RAID 6, RAID 10, invalid disk selection. If we jump over here to the advanced options, there's really nothing over here that you need to do. There is some additional options where it can automatically delete the last LUN or automatically delete the RAID group after the last LUN is deleted. I typically would not set that. I mean, just personally. There's also RAID group power settings. You can allow power savings to be captured on this RAID group as well. And what I think this is the ability to be able to spin down drives if they're not accessed over a certain amount of time. We'll cancel that. So that's storage pools. That's some of the options there for storage pools and RAID groups. We'll also look at LUNs. So we didn't, really what your what you care about most likely, and what your applications and your server admins and your clients and everybody out there is that capacity. You usually have an application on a host. The host needs some level of capacity to be able to read and write its data. So to be able to do that, you need to offer up a LUN, which is a logical unit. To be able to do that, you jump either on the pool itself. So I would go over to the pool, I'd right click on it, hit create LUN. And then this would be how you would create a LUN, a slice of this pool, to be able to divvy off to a host that's connected to the array itself. Now, if I'm selecting, I'm right-clicking and hitting create LUN on the pool itself, it's going to take the properties of that pool for a lot of this information up here. So it's saying, all right, this storage pool type is a pool. Okay, we know that because I right-clicked on the pool. The RAID type is RAID 5. All right, we know that because it's a RAID 5 pool. And then the storage pool for the new LUN, yes, it's going to be pool 0 because I right-clicked on pool 0. So it's giving you information that's already predefined. Gives you available capacity, consumed capacity within the pool itself. Here are where you're going to actually modify the settings to create this LUN. So you can do a thin LUN or not. You can set the user capacity, so I could set it to 1 gigabyte. I could set it to terabytes, megabytes, terabytes, or even blocks. And then I could go in and set the LUN ID as well. And then I can do automated creation of LUNs here. So I could do, I could set it to 10 or 17 or whatever I wanted to. And then if I change that number to anything other than 1, it's going to allow me to assign a LUN name to each one of those. So I could say test LUN, test LUN, leave it at test LUN, and then I create 17 LUNs. They'll all have the name test LUN. And I'll set the starting ID to 1. And then it's going to increment each creation of those LUNs by 1 digit. So first one will come out will be test LUN underscore 1. The next one will be test LUN underscore 2. And so on and so forth. Or you can just automatically assign names and then go back and click the properties for the LUN and then change the name yourself if you wanted to. Very useful command, especially if you're creating a lot of LUNs all at once. Advanced. These are alignment. You may have heard of disk alignment options where you would want to align the disk so that it is on a boundary that it doesn't allow multiple writes to occur on the backend array. You used to have to use diskpart and diskpar to be able to align the LUN itself. When you actually allocate it to a Windows host, you would go and use diskpart, and you would align that LUN so that all writes that occur on that LUN itself are not actually creating 2 writes on the back end. With Windows 2008, that's changed. It's now configured, I think, with a 1 meg offset automatically when you create LUNs, so you don't have to worry about going in and using diskpart and diskpar, or diskpart, excuse me. In previous version it was diskpar. You don't have to go in with diskpart and actually set that. If you're configuring LUNs within vCenter for an ESX server, that's done automatically. So it is stripe aligned when you're configuring within vCenter itself. The default owner here is set to auto, so it is going to do a round robin approach. It does not take into consideration how much load you put on a LUN. So it really is LUN A goes to SPA, LUN B goes to S2B, LUN C goes to SPA. Bad example, I know, but that's how it happens. Just bounces back and forth between the SPs. The tiering policy here, and this is an older tiering policy on VNX OE32. There are some additional options here. This one has not been upgraded, but it does show you the basics here. It does show you that it is an auto tiering policy, or you can set it, you can pin it to the highest available tier if you wanted to. Auto tier will actually, I believe, pin to the highest, and that's what's available in the newest version of VNX OE. It'll auto tier, but it'll pin to the highest, and then it'll trickle down as it needs to the other tiers. So that's it from a LUN perspective, logical unit. Compression and deduplication, I can't necessarily show you those options from this perspective, at least from the block perspective. Now you can compress on the block side. Let me see if that enabler is available here. So if I go to RAID groups and I go to the LUN itself, yeah, it is actually. So yeah, if I go to the LUN itself, and I go to the compression tab, I can turn compression on for a block-based LUN. I've never utilized this option from the block-based perspective, simply because it's meant to be used for data that is not in use. Simple as that. You don't use it for LUNs that are actually being accessed with any kind of regularity. It is more of a, my data is at rest, I want to turn compression on for these LUNs, here's how I do it. That's somewhat different on the file side. Let's see if if we have those options available on the file side for us. So we'll go here, we'll go storage pools for file, and we'll take a look at this storage pool. And I was going to try to show you and see if deduplication and compression was actually enabled within this pool itself, but it is not. It's actually enabled on the file system, so my fault. So we'll go to shared folders, SIFs, and we'll go to one of these file systems, and we'll take a look at a couple things here. Now, compression, really on the file side, compression and deduplication are somewhat one and the same. I don't believe you can set compression on a file system from within the interface itself. If you enable deduplication, it's going to compress those files as well. But this is where you would do it. It'd be on a per file system basis. So you can see right here, it is turned on. I believe it is turned off by default. And then it gives you some information down here, statistics. You know, file scan. It is an operation that takes place on a daily basis. It's not continually run. It's not as data is added that it dedupes. And there's things that have to be in play. There has to be certain access times or modified times that are recognized before it actually goes and dedupes those files, because you typically would not want your files that are being accessed with any regularity to be deduped or compressed, because it does add additional latency to that process. So that's where you would do it from the file side for a file system. The last thing I wanted to touch on here was hot spare, so we'll jump back over to the block side of the house. Go back to storage pools, and your hot spares are configured just like any other RAID group, except you're only selecting one disk, and you're selecting that RAID type as hot spare. So if I go in and hit create, we'll go ahead and create this, or attempt to create it. And I would change, we usually like to put our hot spares in the 200 range, but you could put them wherever you wanted to. I would change this to hot spare. I go in and manually select my disk. That. No need to set it in the advanced option. And then as soon as I hit apply, the disk will show up like this. Once I configure a hot spare, it's globally available to protect any disk that is the same drive type within the array. Another notion is it's got to be the same size or smaller to be able to protect it. So if I've got a 1 terabyte nearline SAS drive out there, I could use a 2 terabyte nearline SAS drive to protect that 1 terabyte drive. I couldn't do the inverse of that. I couldn't have a 1 terabyte drive protect the 2 terabyte nearline SAS drive. So you get the point. It's got to be the same size or bigger to be able to protect the drives on the array. You would also, as I mentioned, you would want to have hot spare for each drive type. So you'll see here I have a drive type for each type of disk, nearline SAS, and flash drive as well. So that's kind of it. That's kind of some of the terminology around the VNX itself. There are numerous clicks and links within this interface itself, which we just won't have time to go over in its entirety. That is the basis of things that I thought were most important when configuring and being in Unisphere itself. You know, it is the ALUA-based capabilities, something you would set when you're zoning in a host to the VNX itself. Your front end and back end ports all available through the reporting capabilities and where you would see that information. The vault drive, storage groups, the creation of traditional RAID groups and storage pools, all useful information when you're doing day-to-day administration. Your LUNs, It's the root of all that is the essence of the VNX, right? That is what you're actually presenting out to the world, to your host in general. Compression and deduplication, these are space efficiency type technology. We took a little bit of a look at that. And then finally, your hot spares. That concludes this lesson of the lab. See you in the next lesson.